Condition for parallel lines. Welcome, everyone. Today, we are going to dive into a very important topic in three-dimensional geometry, the condition for parallel lines. Now, before we get into the complex formulas, let's set the stage. Understanding when two lines are parallel is a fundamental building block for everything else we will do in 3D space. You might remember from your study of 2D geometry that checking for parallel lines is quite straightforward. We simply look at whether the slopes are equal. However, as we move into the third dimension, things become a bit more interesting. We can no longer rely on a single slope value. Instead, we have to analyze the specific direction in which these lines extend through space. Over the next few slides, I will show you exactly how we use direction ratios to determine if those paths are running perfectly alongside each other. Understanding the concept. First, it is important to understand that two lines in three-dimensional space are considered parallel if, and only if, they share the exact same direction. To visualize this, imagine you are walking along one line, and a friend is walking along another. If you are both moving in the exact same direction, or even if you are moving in the exact opposite direction, your paths are parallel. We can also define this using trigonometry. Mathematically speaking, if the angle theta between these two lines is equal to 0 degrees or 180 degrees, the lines are parallel. Now, why does this matter for our calculations? Well, think back to your trigonometry basics. Since the cosine of 0 degrees equals 1 and the cosine of 180 degrees equals -1, it tells us something crucial about the direction vectors of these lines. It means that the direction vectors must be scalar multiples of each other. In other words, one vector is simply a scaled version of the other. This leads us directly into the specific mathematical condition we will examine in the next slide. Now that we've established that 3D geometry requires us to look beyond simple slopes and focus on how lines extend through space, let's dive deeper into the core concept. The mathematical condition. Now that we understand the conceptual idea that parallel lines share the same direction, let's translate that into a concrete mathematical rule we can actually use in our calculations. To do this, let us consider two specific lines, which we will call L1 and L2. For the first line, L1, we have its direction ratios, which we'll denote as a 1, B1, and C1. Similarly, for our second line, L2, we have its direction ratios, represented by a 2, B2, and C2. The core rule you need to memorize is this. These two lines, L1 and L2, are parallel if and only if their direction ratios are proportional. What does proportional look like in practice? It is expressed by this equation. A 1 over 2 equals B1 over B2, which also equals C1 over C2. If you look closely at this equation, you'll see the logic behind it. This proportionality indicates that the direction vector of one line can be obtained simply by multiplying the direction vector of the other line by a constant scalar, which we usually call k. In other words, one vector is just a scaled version of the other. This brings us perfectly to a real-world example of how engineers use this exact principle in construction. Real-world analogy. Now that we have established the mathematical theory and the formula for proportionality, let's step away from the abstract equations for a moment and look at how this concept applies to the real world. Think about the construction of a high-voltage power transmission tower. When engineers design these massive structures, they rely heavily on the principles of three-dimensional geometry. Specifically, look at the vertical support beams. These beams are intentionally designed to be parallel to one another. This isn't just for aesthetics. It is crucial for ensuring structural stability and making sure that the weight, or the load, is distributed uniformly across the entire tower. From a mathematical perspective, an engineer can verify this parallelism by looking at the direction ratios we discussed in the previous slide. If the direction ratios of two different beams are proportional, the engineer has mathematical proof that the beams are perfectly parallel. This ensures that as the beams rise into the sky, they will not accidentally converge toward each other or diverge away, which would compromise the integrity of the entire tower. Step-by-step procedure to check for parallelism. Now that we understand the theory behind why proportional direction ratios indicate parallelism, let's look at a practical, step-by-step procedure you can use to solve these problems every time. I've broken this down into 4 manageable steps so you don't feel overwhelmed by the 3D coordinates. Step 1, your first task is to extract the necessary information from the given equations. You need to identify the direction ratios for the first line, which we call a sub 1, b sub 1, and c sub 1. Then, do the exact same for the second line, which we'll label as a sub 2, b sub 2, and c sub 2. Step 2, once you have these numbers, set up your comparison. You'll create 3 separate fractions by pairing the corresponding components. Specifically, you'll create the ratio of a sub 1 over a sub 2, b sub 1 over b sub 2, and c sub 1 over c sub 2. This represents the x, y, and z components respectively. Step 3, now, simply perform the division. Calculate the numerical value for each of those 3 fractions. Step 4, finally, compare your results. This is the moment of truth. If all 3 calculations yield the exact same constant value, then you have successfully proven that the lines are parallel. However, if even just one of those ratios is different from the others, then the lines are not parallel. We are going to apply this exact 4-step method in the very next slide with a worked example, so keep this process in mind. Worked example. Now that we have understood the theory and the mathematical condition for parallelism, let's put it into practice with a worked example. Here's our problem. We need to determine if these 2 specific lines are parallel. First, we have line 1, where x minus 2 all over 3 equals y plus 1 all over negative 2, which equals z minus 5 all over 4. Second, we have line 2, where x minus 5 all over 6 equals y minus 3 all over negative 4, which equals z plus 2 all over 8. To solve this, we will follow the 4-step procedure I mentioned in the previous slide. Step 1, we need to extract the direction ratios from the equations. Looking at the denominators of line 1, we can see that our first set of direction ratios, a sub 1, b sub 1, and c sub 1, are 3, negative 2, and 4. Now, looking at the denominators for line 2, our second set of direction ratios, a sub 2, b sub 2, and c sub 2, are 6, negative 4, and 8. Step 2, we set up our ratios to check for proportionality. We are going to check if a sub 1 over a sub 2 equals b sub 1 over b sub 2, which equals c sub 1 over c sub 2. Step 3, let's calculate the actual values for each component. For the x component, 3 divided by 6 simplifies to 1/2. For the y component, negative 2 divided by negative 4 also simplifies to 1/2. And for the z component, 4 divided by 8 also gives us 1/2. Step 4, finally, we reach our conclusion. Since the ratio for x, the ratio for y, and the ratio for z are all equal to the same constant, 1/2, we can confirm that the direction ratios are indeed proportional. Therefore, we can conclude that line 1 and line 2 are parallel. As we move to the next slide, I want you to pay close attention, because I will highlight some common pitfalls where students often lose marks during this calculation. Common mistakes to avoid. First, be very careful about ignoring signs. When you are calculating your ratios, a common error is neglecting the negative signs in your direction ratios. For instance, if you are calculating negative 2 divided by negative 4, remember that the negatives cancel out, so the result is 1/2, not negative 1/2. Always double-check your signs during every step of the calculation to ensure your ratios remain accurate. Second, we need to address what happens when you encounter a 0. If any of the direction ratios in the denominator, that is, a sub 2, b sub 2, or c sub 2, are 0, the fraction a sub 1 divided by a sub 2 becomes undefined. In these specific cases, you cannot use the fraction method. Instead, you should switch to the cross-multiplication form. You will check if a sub 1 times b sub 2 equals a sub 2 times b sub 1, and similarly, if b sub 1 times c sub 2 equals b sub 2 times c sub 1. This allows you to verify parallelism without the risk of dividing by 0. Finally, do not confuse parallel lines with coincident lines. While we have been focusing on the direction of the lines, remember that parallel lines can be two distinct lines that never touch, or they could actually be the exact same line, which we call coincident. If you are asked to distinguish between the two, you must perform an extra check. Take a point from the first line and see if it also lies on the second line. Now that we have seen how to successfully solve a problem, I want to pause and discuss some common pitfalls. Even if you understand the concept of proportionality, there are 3 specific areas where students often lose marks. Keep these points in mind as we wrap up our lesson with a quick summary of the key takeaways. Key takeaways. First, remember that the fundamental concept of parallel lines in 3-dimensional space is that their direction vectors are collinear. This simply means they point along the same line or in exactly opposite directions. Second, we have the mathematical test you'll use most often in your exams. The condition for parallelism is the proportionality of direction ratios. As we saw in our worked example, you must check if the ratio of the x components, the y components, and the z components are all equal. Specifically, a 1 over a 2 equals b1 over b2, which equals c1 over c2. Third, keep in mind the geometric relationship. Parallel lines will always have an angle theta equal to 0 degrees or 180 degrees between them. Finally, always remember the underlying logic. This proportionality implies that one direction vector is just a scalar multiple of the other. In other words, you can get from one vector to the other by multiplying by a constant value, which is why the ratios all result in that same constant. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways from today's session to ensure everything is clear before you move on to your practice problems. If you have reviewed these points and feel confident, you are ready to tackle the more complex problems involving coincident lines that we touched upon briefly in our Common Mistakes section. Well done today.